As we saw in the previous unit, datasets are one of the common forms of data returned by monitors. Datasets are used to collect related data into a single object, and they contain two parts, attributes and parameters. Attributes are the main results of interest, and parameters contain information related to the dimensions of the attribute. For example, if the attribute is returned at different positions in time, or over different positions in space, the parameters will contain the time and position variables corresponding to the data points. There are three different types of datasets: matrix datasets, rectilinear spatial datasets, and unstructured spatial datasets. Matrix datasets contain parameters that are not related to position. Rectilinear spatial datasets contain attributes where the data is given on a grid of x, y, and z positions, so the parameters include x, y, and z. This is typically used to return monitor data from FDTD simulations, since monitors measure data on the rectilinear grid of the simulation mesh. Unstructured spatial datasets contain data on a finite element mesh, like the mesh shown here. Monitor data in FDTD solutions will not be returned in the form of unstructured spatial datasets, but you might import data from a finite element solver which will be in this format, such as a temperature distribution profile calculated using the heat transport solver and device. Parameters in an unstructured spatial dataset will include x, y, and z vectors, which give the positions of each vertex on the finite element grid, and a connectivity matrix describing how the vertices are related. This is a visual representation of a dataset generated from a parameter sweep where the radius and height of a rod is varied in the sweep, and the reflection is measured. The reflection data is a 2D matrix, and the height and radius data are 1D. The reflection data is the attribute, and the height and radius are parameters. Since there is no spatial position data associated, this is a matrix dataset. This is a representation of a dataset that contains electric field data from a monitor as a function of space and frequency. The electric field data for each field component is a 4D matrix. In order to represent this in the drawing, the attributes have been drawn as multiple 3D matrices where each contains the data for one frequency point. The x, y, and z position vectors and frequency and wavelength are 1D matrices. The electric field data are the attributes, and x, y, and z and wavelength and frequency are the parameters of the dataset. Since the data is returned over a rectilinear grid of positions, this dataset is a rectilinear spatial dataset. One of the advantages of using datasets is that it's easy to interpret the data when you plot it in a visualizer window, since the parameters and range of parameter values are automatically labeled. The attributes and parameters of the datasets are listed in the visualizer window in the tables below the plot, where you can manipulate which field component to plot and which dimensions of the data to plot or slice. It's also possible to package data into datasets or extract the attribute and parameter data from datasets using the script. The related link below contains a tutorial showing how to package data into datasets and extract data from datasets from the script. And on this slide is an example of a simple script where the electric field components and position parameters are extracted from a rectilinear spatial dataset named E by using the dot operator. Now that we're familiar with the available data types, we'll look at how to access simulation results from the graphical user interface.